So we're going to learn a little bit about heat calculations by looking at this problem. If we have 32 grams of ice at a temperature of 20 degrees below the freezing point, and we heat that up to 120 degrees, how much energy will that process require? In other words, if we look at this is a heating graph, and as we input heat, we see this occurring. The chunk of ice warms up, and once it gets to 0 degrees Celsius, the melting point, the temperature levels off and does not change until all of the ice has melted. After the ice is melted, the liquid water's temperature begins to rise, and this may not be to scale, but here at 100 degrees Celsius, you know what happens. The water begins to boil, and during that phase change, there's no change in the temperature. So the water boils, and once the water is all boiled and turned to steam, if we've contained the steam in some kind of container and we continue to heat it, add heat, that steam will rise in temperature. So we have 5 distinct areas of this graph. The area 1 is the heating the ice, area 2 melting it, area 3 warming up the liquid water, area 4 boiling or turning it all to a vapor, all of the water to a vapor, and then heating that 32 grams of steam up to a higher temperature steam. And so these are going to take different kinds of calculations. For all of the calculations where there is a slope to the line, we're going to be using this. So what this calculation is heat. That's what Q stands for, remember. The heat that is required to warm the ice can be calculated by the mass of the ice. This value called specific heat of the ice, and the temperature change that occurs in this ice. Now, specific heat for any substance is the energy required to change that particular substance, 1 gram of that substance, 1 degree Celsius. So the units are always right here, joules divided by gram and divided by degree Celsius. So if we substitute in our values from our problem, we have heat equals 32 grams times the specific heat of solid water or ice, and we looked this up on the internet and found this value, and the change in temperature from 0 to 20 degrees, negative 20 degrees to 0 is a change of 20 degrees. So that gives us a product of 1,312 joules. Now if we move on to area 2 of our graph, area 2 is a phase change area, and the energy that goes into changing the phase is, in this case, we're melting the ice, the stuff that's fused together. If we reverse this reaction, we'd be freezing the water and turning it into ice. That involves this enthalpy of fusion. Now the enthalpy of fusion times the mass is going to give us the energy it takes to melt the ice. And so what we're really talking about here is H2O as a solid going to H2 as a liquid, and the enthalpy of that reaction is 333.55 joules for every gram of ice that we have. So we multiply those and we get this product for the second part of our graph. In the third part of our graph, we're heating liquid water, And so the heat required to change the temperature of that water is the mass of the water times the specific heat of liquid water, that's the 4.18 joules per gram degree Celsius, times the change in temperature. And that gives us 13,376 joules for the third area of the graph. For the fourth area of the graph, we are boiling the water, turning it all into vapor. So that's going to involve the enthalpy of vaporization. So the heat required to boil all that water, turn it into a vapor, is the mass times the enthalpy of vaporization, and that is 72,224 joules. Then, to heat up the steam, is the heat required to change the temperature of the steam is the mass of the steam times the specific heat of steam, which we also looked up on the internet, times the change in temperature, and it went from 100 up to 120. So if we add all of these together, these 5 products, we will be able to tell the answer to our original question, which was back here: how much energy does it take to do this process?